Hi, my name is Daisy, and I'm going to walk with you today through a combined spectral problem. And this one just happens to be sec J, I guess, for our unknown. This substance has 10 carbons, 12 H's, and 1 oxygen. First, we have our three spectra. So we have an H NMR, a C NMR, and our IR spectra. So first we're going to look at our IR spectra, which first we can determine which bonds are in our substance that we don't know. So if we look at the 3000 wavelength number, here is our CH range. Anything higher than this is usually has an H attached to it. We see that there's no section in the 35,000, which is usually an OH, and we see that it does not have that. So, as it is not a deep, wide peak, we see that it is a CH bond, not an OH. Then we'll move on next to our double bond region, which we can see, because it's from 15,000 to about 18, so 1800, 1500, 1800. But it is at about 1750. This one here, we can see that it is deeper, and the C double bond O stretch is usually deeper than a C double C carbon stretch. And we see that it has both. So when we look at that, we see that it has both the C double O and the C double C. And then the next region, we are able to see that there's nothing else extra sticking out, but it is our carbon-carbon bond range, which it does have. So next, we see where our other spectra aligned. So that was our IR spectra. Next, we are going to look at our CNMR spectra. So here is the most electronegative, it's downfield. Here is our upfield. We can see that our C double bond O appears here on there, and that is not the right thing. We see in this summary of chemical shifts that C double bond O shows up higher, and then we are able to see where our other stuff aligns. So with that, we see that it does have the three peaks here, as being our carbon-carbon bond and our aromatic ring, which is a little different. So we see that it has, because this is our carbon-carbon bond, and it signals for a aromatic ring or a benzene or phenol in there, and it has 3 carbon, double bond carbon, it's in there. So we have 1, 2, 3 peaks. And then the next part we look at is our carbon-carbon bonds, which are here. We see our sp3 carbon and our C bonded to C carbon, which is a little bit more, it's shifted. But that one is shifted, we can see, because it is close to this carbon double bond oxygen. So that is why that is shifted past the 40, which it isn't usually. It's because it is next to the carbon with our oxygen. And then the next thing we look at is our HNMR spectra. So we have, if we look closely here, we can see that we have a doublet here. So 1, 2 peaks. We have a sextuplet here. 1, 2, 3, 4, 5, 6. That would be a sextuplet, and we have a singlet here. Just a single peak. And then with our indicating integrations on here. So there's 5 carbons that have a doublet, 4 with attached to a sextuplet somehow, and then one singlet, or three with a singlet, I guess. Then that leaves us to look at our degrees of unsaturation here. So the next thing was we have our molecular formula here that was given to us to start off with, and we look at this and compare if we're going to look at our degrees of unsaturation. I've inputted a little formula here for us to look at. So you have, you know how you get the amount of hydrogens first fully saturated. It is the amount of carbons times 2, so that'd be 20 plus 2 for that extra 2 carbons at the end. So that would be where we get our 22 here. And then minus, we only have 12 on our compound compared to what it would be the 22 if it was saturated. That equals 10 divided by our 2 to figure out how saturated it is, and that comes to 5. So there's 5 degrees of unsaturation, so not every bond is saturated, we're able to see. Hopefully here we can compare our frequency to our functional groups. So like we talked about, the 29,000 to 31,000 stretch, that would be our CH. Our 1725 stretch is our C double bond O. Our 16,000 peak is our C double C bond. And everything under our 15,000 was our carbon-carbon bonds. And then the next we'll look at where our chemical shifts show up on the CNMR. So when we look at that, remember we had the aromatic ring. So that means that was our 3 C double bond C's that help make up our ring. We have our 207 or C double bond O, which makes sense because it is the most electronegative because it has the O, which makes it more downfield. And then the carbon that is next to that C double bond O, that next one, is going to be shifted, which is why it shows up as higher in our chemical shift than where the rest of them are, because the rest are about the same. So then next we're going to look at our chemical shifts. So we have where they showed up on the map, are 7.2-ish, about 2.7 or 2.1, where they show up on our parts per million in our H&MR. So we see that there is a doublet. So that would be, they're all kind of by one other one, our H's here. And they're all in the same, because similar. And then we look at, and there is 5 H's here. 1, 2, 3, 4, 5. That is where we get our integration number. And then next, there is 2 H's on each of these carbons, which is where we get our 4 H's. And it's a sextuplet because they are in the same chemical area. Same chemical area. So there's 2 carbons here and 2 carbons here. This carbon doesn't see any carbons here, and it sees a carbon here. Or 2 carbons here. So that way makes it a triplet. And then the same carbon, or the other carbon that we just looked at, is only able to see that other carbon, which is also a triplet. And because they're in the same chemical combinedness, togetherness, it is a sextuplet, not 2 triplets. And then off of our 3 H's here, off of our carbon, with our ketone here, we are able to see that it does not see any other carbons, so it is a singlet, which leads us to our compound, which is our phenol here. So off of 1, 2, 3, 4, our phenol connects to the 4th one. And then, so that's 4-phenyl. And then our ketone here is on there too. So 4-phenyl 2-butadiene is our compound. Thank you.